Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'll be covering limiting reactants, theoretical yield, and percent yield. Let's get started. If you recall on the previous video where I covered reaction stoichiometry, we talked about how important it was to actually balance an equation first before you get ready to get started. Now, one of the things you may have noticed is that in all the problems that we did, there was only information provided about one of the reactants. So it made it very easy to decide what our starting point was and could therefore predict how much product we could expect. However, there are situations where you could face problems that have information about multiple reactants. And so you want to know how to actually attack that. Now, I want us to step outside of the chemistry lab and into the kitchen to understand this next concept known as limiting reactant. So like many of you, I've gone downstairs and wanted to cook some pancakes or some waffles at some point in time. However, when I look at the ingredients that are needed, let's say for making waffles, perhaps it says I need 2 eggs, a cup of flour or a cup of the powder, and then some amount of water. But when I get down to my refrigerator, I realize perhaps I only have 1 egg. Now, having only 1 egg does not stop me from making my waffles, but what it does do is limit the amount of product or the waffle that I can create. So that means in that scenario, my eggs, my flour or powder, and my water, the egg is considered to be a limiting reactant. And because it is in a limited amount, it's going to dictate how much product I can actually produce. Now, that same theory happens in the chemistry lab. And so when you have reactions that require or have multiple reactants, it's likely that one of those reactants is going to be completely used up before all the others. Like if we parallel that to the waffle example, the egg would be completely used up before we get through the flour, powder, or the water. And so the element, the reactant that is actually completely used up, that is what is going to determine how much product we can make. And so the reaction will stop and then no product is being made because you've ran out of one of those starting ingredients. And so this reactant is what we're going to be referring to as our limiting reactant. And a good clue that you'll know you're dealing with one of these problems is that you may have information about 2 or more reactants provided for you in the problem. This may also be called a limiting reagent problem, so just be on the lookout for that. But in this type of problem, one of the reactants will be completely consumed and the other one remains in excess. And so we'll call that our excess reactant. Now, it's very important to note when you're trying to figure out which or how much of a certain product will be made, you base it off of the amount that the limiting reactant predicts. When you're faced with doing a limiting reactant problem, you're going to have to actually do this problem twice or however many times as reactants provided to solve for your answer. Once you figure out what amount can be provided by both starting points, you then choose the lowest amount as your theoretical yield. And so let's try this problem, for example. It says how many moles of Si3N4 can be made from 1.2 moles of Si and 1 mole of N2 in the reaction. And so in this case here, we're looking for moles of Si3N4. And what we know is that we have 1.20 moles of the silicon and 1.0 moles of the nitrogen. And so as you can see, you have information about both of the reactants. Now, what you may notice, it doesn't say, hey, this is a limiting reactant problem. You need to deduce down the fact that you have information about 2 of the reactants. You're going to want to solve this problem twice with each one of those reactants as the starting point. And so if we go through our example, we take 1.20 moles of Si. And our first step is to get to moles. So we'll go moles of Si on the bottom and moles of Si3 and 4 on the top. And then we fill in with our coefficients as such. And so we would say 3 on the bottom, 1 on the top. And when we plug that in, we end up with 0.400 moles. Now, if you're doing a multiple choice problem, and you see this as an answer, you can be very tempted to say, oh, I'm good. I see the answer. This has to be it. Well, it's a possibility that it's the answer. However, we need to do this problem 2 times, starting with our other reactant, and then we'll choose based on which one produces the smaller amount. And so we could take 1.0 moles of N2, and now we're going to solve for the exact same thing. And so on the bottom, we put moles of N2. On the top would be moles of Si3N4, and we fill in as 1 and 2, those numbers coming from the coefficients, and then we plug it into our calculators and we get 0.500 moles of Si3N4. Now, based off of this, we would then say that this lower amount represents the theoretical yield. And therefore, the silicon would represent our limiting reactant, and the nitrogen would represent the excess reactant. What this means is we physically don't have enough silicon present to make up to that 0.5 amount that's being predicted from the other starting point. And so therefore, silicon is considered to be the limiting reagent or limiting reactant, and then nitrogen is the excess reactant. Make sure when you're applying those terms, you apply them to the actual reactants and not the product that's produced at the end. So again, just revisiting some of the verbiage, the theoretical yield is the maximum amount of product that can be produced, and that's based off of the limiting reactant. Now, occasionally with these problems, or if you actually are stepping into the lab, you may be asked to determine something that's called the percent yield. And the percent yield is basically saying, we know how much we were supposed to get, but when we actually went in there and did it, this is how much we got. If we compare those two to one another, how good did I do? And ideally, our percent yield will end up being a high value, like 100% yield would be awesome. That means all of what I was supposed to produce, I actually did. But for whatever reason, just like when you're making waffles or pancakes in the kitchen, you may not actually make the predicted amount. And so when you're in the lab or when you're reading the problem, the amount that you actually obtain in the experiment represents your actual yield. And the formula for your percent yield would therefore be the actual yield, what I actually got, divided by the theoretical yield, what I was supposed to get, times it by 100. Now that formula, you may look at it like, oh, I've seen this before, and you've actually seen something that's similar to it, but not quite the same thing. What we were presented with in chapter 1 was percent error, and percent error is your actual minus theoretical over theoretical times 100. And your percent error is basically saying how bad did you do. You want a low percent error. You want close to 0%. Percent yield, though, is slightly different. So that's your actual divided by your theoretical times 100. And we want high percent yields. And so when you're solving for this type of problem, you want your actual and your theoretical yield to be the same units, because we're comparing those two to see how good did I do. And so let's try a problem here. It says when 28.6 kilograms of carbon are allowed to react with 88.2 kilograms of titanium 4 oxide in the reaction below, 42.8 kilograms of titanium are obtained. Find the limiting reactant, theoretical yield, and percent yield. Okay. And so we have the information that's provided for us. And I'm just going to take and write this equation out just so I have some room to work. And again, I like to draw my mole bridge that I discussed in the previous video. So it helps me focus on the parts of the reaction that I care about. And so we have 28.6 kilograms of carbon, 88.2 kilograms of titanium, and it's telling us 42.8 kilograms of titanium are obtained. And so this number here represents our actual. What we need to figure out is theoretically how much we supposed to get based on these two starting points. And so if we continue with our mole bridge calculations, we would start with 88.2 kilograms. And now you'll notice that we can now combine doing unit conversions with that metric system along with this stoichiometry stuff. And so our first step is to go from kilograms to grams in this case of titanium 4 oxide. And we know that in 1 kilogram, there are 10 to the third grams. And then we would go from grams of TiO2 to moles. We know that's the linking unit that we want. And we'll check the periodic table to calculate that molar mass. So we take 47.867 plus 32 for the oxygen, which is from the 16 times 2. And so that gives us 79.867 grams is to 1 mole. Next, we then do our mole to mole ratio. We cross that bridge. So it's 1 mole of TiO2 to every 1 mole of Ti. And then now we can go to grams using the molar mass. So 1 mole of Ti is to 47.867 grams of Ti. And then last step would be to get that to kilograms. So grams of Ti to 1 kilogram of Ti. And we know it's still 10 to the third. Now, when we plug this in, again, those 10 to the thirds, they drop out. So you can plug it in and just say 88.2 times 47.867 divided by 79.867. And what we end up with is 52.9 kilograms of titanium. Again, this could be our answer. However, we have to do it both ways to ensure that indeed we can identify what our limiting reactant is. And so we start with our other given, so 28.6 kilograms of carbon, and our steps are going to be exactly the same. So our first step is to go from kilograms to grams, so 1 kilogram of now carbon is to 10 to the third grams of carbon. And then we now go from grams of carbon with its molar mass to 1 mole of carbon. We then want to cross the bridge, so mole to mole ratio. So moles of carbon, which are 2 for every 1 mole of titanium. And then the last part of the calculation is exactly the same for what we've already done above. So we would just write those exact same things. We want to make sure when we're solving these limiting reactant type of problems, each time we make sure that we are solving for the same thing so that we can easily compare the two values to one another. And then the last step is getting to kilograms. And so now when we plug this in, 28.6, again, I'm going to cancel out those 10 to the third, so I'm not going to worry about putting them in. So 28.6 times 47.867 divided by 12.01 divided by 2. And that gives us 56.99 or 57.0 as our answer. So when we think about what our theoretical yield is, well, the theoretical yield is that smaller amount. So 52.9 is our theoretical yield, which makes the titanium our limiting reactant. And therefore the carbon is the excess reactant. If we want the percent yield, now we're going to take the actual, which was stated above. So 42.8 divided by 52.9. Again, make sure you're picking the theoretical yield. And then we're going to multiply all of that by 100. And so when we plug that in, we end up with 80.9% yield, which isn't too bad. Ideally, we want to be close to 100 when we're getting our percent yield out. Okay, next up, it says how many grams of N2 can be made from 9.05 grams of NH3 reacting with 45.2 grams of CuO, and the reaction is shown for you. And so again, if we look at what we're given, we have 9.05 grams of the ammonia and 45.2 grams of copper 2 oxide. We want to know how many grams of nitrogen can be made. So when I think about connecting my bridge, I'll be going from ammonia to nitrogen, as well as copper 2 oxide to nitrogen. Make sure you solve for the same thing each time. So we start from the beginning, 9.05 grams of NH3. Our first step is to get to moles, once again, using the molar mass. So grams of NH3 on the bottom, moles of NH3 on the top. We know we're going to pull this from our periodic tables. And so that should be 17.04 grams is to 1 mole. Next up, we then do our mole to mole ratio. So we would say 1 mole of, not one, do like me, do like what I say to do, write the units first. Moles NH3 is 2 moles N2. Now let's go in and add the coefficients.
I can't get the answer to that on HomePod.
Now let's go in and add our coefficients. So we'll put a 2 on the bottom, 1 mole on the top, and then continue on to our grams. So moles of N2 on the top and grams of N2 on the top. Excuse me, moles of N2 on the bottom, grams of N2 on the top. And so that would give us 28.02 grams for every 1 mole. Plug that in, 9.05 times 28.02 divided by 17.04 divided by 2, and that gets us 7.44 grams of N2. Again, if there's a multiple choice question, don't just jump the gun and think that this is the answer. We have to solve this problem twice. So we pick 45.2 grams of CuO. Same exact steps. First step is get 2 moles first. So grams on the bottom, moles on the top. If we calculate the molar mass for our copper 2 oxide, copper, we take its mass plus oxygen, and we get 79.546 to 1 mole. Next step, mole to mole ratio. Moles on the bottom of CuO to moles on the top of N2. Fill this in, we have 3 moles, these are the coefficients, to 1, and then we solve for the exact same thing. 28.02 grams of N2, and on the bottom, 1 mole of N2. Now when we plug this in, 45.2 times 28.02 divided by 79.546 divided by 3, what we end up with is 5.31 grams of N2. So if these are the 2 answers you get, which would you pick as your theoretical yield? Well, again, it's going to be that smaller amount. That would become your theoretical yield. This one would end up being our limiting reactant, the copper 2 oxide, and making ammonia our excess reactant. The final thing to do is calculate the percent yield, and it says if 4.61 grams of N2 are made, what is the percent yield? And so this represents our actual. So for the percent yield, we're going to take the actual, which is 4.61 grams, divided by 5.31 grams, and we're going to multiply by 100. And when we do that, we end up with 86.82% as our percent yield. I hope this video helps you understand limiting reactant, theoretical yield, and percent yield. Be sure to like, comment, and subscribe, and let me know what other content you would like to see. Have a great day, and I'll see you guys later. Bye-bye.